goes through over here, and it also goes through, if I can find where I'm going, over here, and one more over here, and that's 3 of them. Perfect. That's everything we need. So now, if you look again, there is another mixer here, another mixer here, another mixer here, and that finally brings the signal down to 80 kilohertz. Now we're within the IF bandwidth of the instrument, but that requires yet another PLL, and that PLL is over here. And that would give us the signal necessary to connect to these 3 mixers, which then bring it down to 80 kilohertz. Now, there is a bunch of calibration signals and so on are also generated internally. That's how the instrument can self-calibrate in order to make sure that it has the right frequency sampling and so on. So having said that, I'm running out of breath here. Having said that, the 380 kilohertz signals, which are derived from all of these, is actually, let me just connect them here for the sake of completeness. There we go. These 380 kilohertz signals are now sampled by synchronous samplers over here, which are driven from the 10 megahertz signal with an IF sync signal, and that would generate 6 DC signals. After all of this, these 6 DC signals contain all of the real and imaginary values required to compute full 2-port S parameters. They go through sample and hold, and there's an analog to digital converter which sweeps these one at a time and measures them all. That's why the sample and holds are there. And finally, from that, we can compute through this so-called quiet bus, which is just a digital bus. It can finally compute the 4 S parameters that are required to get the signal that you're looking for. So the 4 S parameters are computed through this path. So where does the YIG get locked? Well, that is also fairly easy to follow. So the YIG goes through here, goes over here, it gets down converted, and look at that, there is source lock signal here, which is derived from the output of this mixer, and that source lock signal is then taken over here, goes through this other phase frequency detector, and then it goes through here, and then finally goes through here and locks the YIG. So the YIG is locked through this path, but this path needs this to be locked and this to be locked, but not this one, because this one generates the 80 kilohertz signal. We are looking at the signal before these mixers, so we don't need the output of these, which means that if our YIG oscillator is not locked, either this is broken, this is broken, that's broken, or this broken, or the clone generator, or any of the mixers that are required to bring the signal down. So there is a lot that can go wrong here. Now, having said that, pay attention to the fact that all of these signals are actually locked to the same 10 megahertz. You see 10 megahertz here, same 10 megahertz here, 10 megahertz here. Here's the other 10 megahertz. Here's the other 10 megahertz. Here's the main crystal of the unit. Here's the 10 megahertz. And you can see that all of the PLLs use the same main 10 megahertz of the instrument. So now, because these are each their own units, we can actually look at these signals individually and find out which of them is not locked. Now, I've been playing with the instrument a little bit, and the initial phase lock problem I actually accidentally almost resolved. And I'll tell you how I resolved that. This is a very subtle point. The YIG oscillator has a fine tune and a coarse tune. The fine tune is done by the FM driver, and you can see that it has a slope of -6 megahertz per volt, and that is what's controlled by the main PLL loop. But there's also a coarse control, and that coarse control is being, let me change the color here. That coarse control is actually driven by this A to D converter, by this D2A converter and a coil driver. Now this D2A and the coil driver have a digital word that comes onto it, which then tells the YIG oscillator to roughly where to go, depending on the desired operation. But let's say that you want to lock it at one, let's say you want to lock it at 10 gigahertz. This will put it very close to 10 gigahertz, let's say at 10.1 gigahertz. And once it's at 10.1 gigahertz, the FM driver in a closed loop system will then lock it perfectly to 10. gigahertz. In my unit, because the battery had run out and the memory was flushed, the calibration file for this D to A converter was lost, but it was stored on the hard drive. I actually restored it, and that caused it to come back to being roughly in the right frequency. So now it logs, but not all the time. There is still a minor problem where it occasionally seems to lose log, and there is some problems, jittery problems with the signal coming out. So having gone through all of this, I hope you're still here. I would love to hear if you actually listen to this entire block diagram description. I'm going to now go back to the instrument. I'm going to identify some of these blocks, and I'm going to show you the problem. It may not be a serious problem, but it's still worthwhile investigating. So let's go back to the unit. And here's the shot I'm sure you've been waiting for to see. This is now looking at the other side of the instrument. Remember that the front of the unit, the Yiga oscillator, which is right actually behind this. This is the floppy drive here. So on the other side of this, the Yiga oscillator, the push down converter for the low frequencies, as well as the main filter bank was located. So we've seen it already. So remember that stuff's over there, and all the other microwave components are here. We can easily follow them. So this is port number 1 over here, and this is port number 2 over there. And you can see that here's the coupler for port A, here's the coupler for port B. Here's the step attenuator for one of them, step attenuator for the other one. Here's the bias D for the first port, here's the bias D for the other port. Here's the main transfer switch that switches the order in which the signal goes in and out and selects between the reference as well as the reflected power. Here's the main power amplifier, which drives the step recovery diode and the converter mixer, which is all located in this block. Behind it is the main mixer for the main portion of the IF. You can see that the test signal for port B, the reference signal for port B, test for port A, and reference for port A are all handled in this little microwave unit here. So the signal that comes into the power amplifier for the step recovery diode is coming from one of the synthesizers. So this is one of the signals of interest to take a look at. There's also another signal which then enters this block at the top, and that's the one that drives the second banks of mixers, which brings the signal down to 2.5 megahertz. So that's the other one that's of interest to look at. Obviously, all of those signals are going to come from the boards that we saw on the other side of this main motherboard, and that's where everything is handled. And here's Pooch checking everything out there. So you can see that all the boards that are over there are going to be our main synthesizers and PLLs, and those signals are fed over here. And the IF signals, once they're generated down to IF frequencies, where then go through the A to D conversion, as I explained, go back onto those boards. And everything else is really pretty straightforward. There's nothing surprising here. The power supply is right over here. The main big fan is over there. But the signal path, no pun intended, is all clear. So the very first thing to do is to look at the signal coming out of the instrument. So I can actually show you what the problem with the phase loop actually looks like. And then we have multiple points in here which we can monitor to find out which of the PLLs is causing that little instability in the signal, which I'm not even 100% convinced might be an issue, but I think it shouldn't be doing that. Anyway, let's go and take a look at it and we'll find out. And we have 3 points of interest in here to take a look at afterwards. Here we go, everything's turned on, and you can see that the error is gone. And right now I have port 1 connected to the input of my Keysight EXA signal analyzer, so we can take a look at the signal coming out. And look, it's measuring the 4-port S parameters and doesn't give me any errors anymore after I fix the Yiga lookup table. And you can see that, remember, this network analyzer right now is not calibrated, so I haven't done S parameter calibration, so these measurements are very crude. But you can already see that the S11 is all gathered near the center point here, which is 50 ohms, which makes sense because the input of the spectrum analyzer is 50 ohms, and S22 is open, so it's all rotating around the output outside of the switch out there, and the S21, S12 are obviously at minus infinity in theory. So it is working, at least it looks like it's correct. It's not generating any errors or anything like that, but let me show you the signal. Now, in order for us to see the signal, it's going to be very difficult as it's switching. So I'm going to put it into CW mode. First thing I'm going to do is I'm going to stop it from switching back and forth between the different forward and reverse path. You can see the light going back and forth. So it's going forward and reverse path. That's how it's measuring all the S parameters. So let's go ahead and change that. I'm going to change that so that we only measure a single channel. So now it's only measuring S11. And you can see that it's close to 50 ohms without calibration. And I'm going to also change that to CW mode. And let's look at
something around, right now it's doing 40 megahertz. So you can see that 40 megahertz is right in the center here. So let's look at 4 gigahertz. So we are somewhere within the band of the gigahertz. They're nice in the beginning, but there is our signal. You can see it's right there, and it's indeed, it cannot do exactly 4 gigahertz because it has limited frequency steps. Right now it's at 3.9821. So we can go a bit closer over here and take a look at the signal. You can see the 4 gigahertz signal is indeed coming out. So let's zoom into here and see if there are any issues. So here's our signal, and at first glance, it looks okay, sitting at 3.982 gigahertz, which is what the instrument does because of its finite steps. And if I go ahead and change the span and look at the signal closer, you can immediately see the problem. So there is indeed something going on. This PLL is continuously coming in and out of lock. Now, it may be that this is normal and the instrument has some internal steps that is going through, and in between when the PLL isn't completely locked, it doesn't care anyway, because the unit is not generating any errors. You can see it's perfectly happy with generating the 4 gigahertz signal right there, and it doesn't give me any problem. So I'm not 100% sure if that's an issue, but it could be. So nonetheless, even if it's not a 100% issue, it would be cool to try and trace it and find out which of the PLLs is coming from. Because if we can detect it, then we really understand how the instrument works, and that itself is quite rewarding. So as I mentioned, a couple of different places to look for various signals. There's a couple of signals that going, different PLL signals going to different places. Obviously, the easiest one to look for is the one that goes through the power amplifier. Now, in order for me to detect the lock, what I'm going to do is I'm going to leave the instrument in the same CW mode as it is, and I'm going to disconnect it. I'm going to connect it to a frequency counter, which can tell us how stable that frequency is, a little bit easier than it is on the spectrum analyzer sometimes. So we can look at that on the frequency counter and see how stable that signal actually is. First thing, let's measure the internal 10 megahertz crystal of this unit just to make sure it's nice and stable. And then it's easy to do. I'm going to use my HP 53131A, which is a frequency counter that I upgraded in the previous video with the 3 megahertz expansion over there. We're going to use that and try and measure the 10 megahertz reference. That's pretty easy. So let me go ahead and plug this guy in, which is all the way at the back over here. There you go. That takes care of that. And not too bad. Check it out. We're looking at 10 megahertz and then 2 hertz off or so, which is not too bad. And that is very, very stable. You can see that it's not really moving around. Only the smallest digit is jumping around, which is totally normal. So I'm not worried about that. That means that we can move on. So the next thing we can take a look at is a signal coming from our first PLL. It's the first synthesizer going into the power amplifier, which drives the step recovery diode. Let's take a look and see how stable that frequency is. That's also part of the loop. And we can do that by disconnecting it and connecting it to the frequency meter over there. I have to cycle it out because I don't want to disconnect it and have it floating for some time before I can connect it. So let's go ahead. All right, here we go. We're nicely connected once again. The instrument is set to CW mode at 4 gigahertz. So now I am measuring the frequency of the first synthesizer. And check it out. 508 megahertz.
Shit.
Very, very nice and stable. It's not moving around at all. So that's indeed not a problem. So our first synthesizer, which I showed you, which had about 500 megahertz range, and that makes sense also, has no issues. It's very stable. So we can eliminate that as an unknown. Now, the second synthesizer is the one that down converts from the 80 something megahertz down to 2.5 meg. But if the frequency of the unit is set to below, I can't remember exactly how much it was, below 200 megahertz or so, then the step recovery is actually disabled and it will directly go through, which means that if the unit is set to 40 megahertz, I expect the second synthesizer to be at 42.5 megahertz. So we can measure that exactly. So this is the next thing I'm going to do, disconnect that, connect it back to this, measure the frequency one more time, and see if that makes sense. And once again, now we're connected to the other synthesizer. The instrument is set to 40 megahertz. And you wouldn't believe it. There it is. I found the problem. Check it out. It's supposed to be set to 42.5, exactly what I said based on the block diagram. But check it out. It's not very stable. And that's exactly what we see on the spectrum analyzer when we see the frequency jump around. It's coming from the second synthesizer. So we've nailed it down. It's not a problem with the EGOT filter. It's not a problem with the reference with the first PLL. The second PLL is messing up. Unfortunately, the second PLL is also the most complicated PLL. It's the one that has an internal mixer and so on. So again, as I said, I'm not 100% sure if this is even an issue. For all I know, this could even be either dithering or just simply be jumping between the points. Although I'm not fully convinced. But anyway, we can nonetheless go ahead and remove that board and take a look at it just to see what it looks like, even if you don't fix it. So before I try and fix that board, I'm going to try and do a calibration of the unit and actually measure something. But before that, let's flip it to the other side, take the board out so we can see and at least take a look at the PCB. And our second synthesizer board is board A2, which we can go ahead and unplug. I actually unplugged it and then accidentally erased that video. So I'm doing this the second time. And let's go ahead and take that out. And I've gone ahead and taken the shields out of it as well, so that we can take, a closer look at it. So let's see what's on this board. Now, if you forgot what the block diagram looks like, make sure you go back in the video and take a look at the block diagram, because it's really hard to get everything here in frame. So I'll just quickly explain what's going on here again. So if you remember that PLL had either a divide by 2, 4, 8 output or a straight through output. So here's our divider that can be programmed for different division ratios. Here's our selector switch, which then selects. So the output of this entire section, which are 2 VCOs and our mixer, here's our first VCO, here's our second VCO, here's our mixer. The output of that goes through this divider and then selected via this selector here, and that jumps to this cable and then goes through here and goes back out of the back of the unit, and that was the signal I was measuring. So I was measuring the output of this from the other side of the network analyzer, and that's what was jittery. So somewhere along in this area, probably is something that might be either doing it on purpose, or that there's occasionally locks and locks back, unlock and lock mechanism, which sometimes happens to PLLs when they're not operating perfectly near where they like to be in the closed loop. So one of these components could be bad, but honestly, only if you guys are really interested in me going through the repair of this, I'll go back and do it. Otherwise, let's put this back together. It seems to be happy with the way it is right now. We can do an S-parameter calibration and see if we can measure something, because that's really the real test to see if it works. But I know which card it is, I know which output it is, I know the exact symptom, and you figured all this out by going through the block diagram step by step and using some intuition on which signals to take a look at. And that's one of the messages I wanted to get across. So if you really want, we can go through the detail of this and find the problem by bringing the wires out. The problem is that obviously I cannot probe this while it is operating. It has to be inside the unit. And as soon as you put it in here, then you're running into the problem of, how do you access all this once it's inside? So you know how it is. And so as a result of that, only if you're really interested will I dig into it. So let's jump to the S-parameter calibration. So I went ahead and I put the instrument to a 12-term regular standard calibration with my calibration kit over here. And it's a manual calibration routine. And you can see I'm also connecting it now to a bandpass filter, which is adjustable to measure its S parameters. And check it out, it works beautifully. The calibration was successful. I verified the calibration afterwards with some standard loads, and it was good. So it looks like that there is no issue that I can detect, at least. Either the problem we're seeing is intentional for dithering, or that it doesn't really affect the performance because it's in between the measurement points. But so far it looks good. So let's take a look and see what we're looking at here. So I changed the display type here to be just the magnitude of all the S parameters. So I'm not showing it on the Smith chart anymore. So it's a little bit easier to relate to on these plots. And here's S11, S22, S21, and S12. And right now the filter is set to 2.5 gigahertz. It's a bandpass filter. And you can clearly see from the S21 that we are letting the 2.5 gigahertz signal through, and we are attenuating it right outside of 2.5 gigahertz, but a little bit higher. And we have another mode where the signal leaks through once again. So outside of the frequency of interest, outside of what it is specified, it doesn't behave very nicely. But you can see that it is really well matched right at the frequency that it's supposed to operate. So right at 2.5 gigahertz right now, we have a nice deep notch in the S11, and S22 is symmetric, and of course the transmissions are also perfectly symmetric. I can go ahead and change the frequency. For example, I can increase it to 3 gigahertz, which is this upper frequency band, and you can see the S parameters shift with it. Quite nice. And right outside again, we have this issue, which is undesired. And let's go back all the way to 1.5 gigahertz, and you can see here at 1.5 gigahertz, it behaves quite nicely and behaves quite differently again. So it looks good. I should say I'm pretty happy with it. So whatever the problem is, again, it's not an issue or it's by design, but I would love to hear what you guys think. I think we covered a lot of material. The block diagram, really understand the instrument is very, very helpful. And if you guys like it, please let me know. These videos take a long time to produce, especially during repairs and during the reviews that I do. So let me know if you enjoy it. It's always nice to hear from you, and we can continue the discussion in the comment section.